In the mid-1890s, the United States Navy stood at a crossroads of fire and steel. They were a force clinging to the remnants of the Civil War, watching from the sidelines as European powers launched ironclad behemoths that redefined the nature of conflict. To compete, they needed a breakthrough. They needed the ultimate warship. But in their race for innovation, they produced the Kearsarge-class battleships, which hit a controversial design choice that sparked a fierce, decades-long debate about the very nature of naval supremacy. The design was revolutionary. Navy engineers, eager to modernize, decided to challenge the conventional wisdom of naval architecture. They would not just place guns on the deck. They would stack them. They called it superimposing. By placing a smaller secondary turret directly on top of a larger primary turret, they intended to maximize firepower on a compact platform. On paper, it was a triumph of efficiency. It was elegant. It was intimidating. It was meant to be the future of the fleet. But the blueprints faced a chaotic, violent reality at sea. To understand why this happened, you have to picture the atmosphere in the shipyards of the late 19th century. The air was thick with the scent of coal smoke and molten metal. There was a desperate, feverish energy driving these men. They were not just building ships. They were building the foundation for America's rise as a major naval power. Every engineer felt the weight of national pride on their shoulders. They were working with limited space and near-unlimited ambition, but in their drive to innovate, they made a decision that would haunt the naval community for years. They attempted to solve the problem of limited deck space by pairing two different calibers on a single mount, forgetting that in the heat of battle, a ship is a living, vibrating, complex organism. They began with the turret structure. To maximize efficiency, they designed a system where the secondary turret was mounted to the roof of the primary turret, sharing a single rotation mechanism. It was a masterpiece of geometry. But as soon as the designs were unveiled, a question burned in the minds of veteran gunners. What would happen when the cannons fired? The answer became a point of intense contention during the early service life of the Kearsarge in Kentucky. The crew prepared for target practice, their faces masks of professional intensity. The officers on the bridge stood stiff, waiting to test the capability of their new ships. The signal was given. The primary batteries thundered, a roar that shook the deck. The air was instantly replaced by thick, sulfurous smoke. Then, the critique began. The gunners reached for the controls to align the secondary battery, only to realize that the interconnected system created significant operational limitations. Because the turrets were forced to rotate as a single unit, the gunners could not independently train the two gun calibers onto different targets. Coordination was hampered by the shared rotation, and the complex ammunition handling proved difficult under combat conditions, where blast effects from the primary guns further complicated fire control. It was a nightmare of mechanical dependency. They had designed a system where the secondary gun's utility was tethered to the primary turret's position. The gunners could not aim both sets of guns independently. They were locked into a single firing solution. The most advanced ships in the U.S. Navy were, for many critics, a tactical compromise that limited the ship's versatility in a chaotic, multi-target engagement. The officers and designers eventually faced the reality that while the ships were formidable, the superimposed design created a bottleneck in fire control. But what was it about their ambition that made them push this design despite the vocal warnings of the era? And what happened when the High Command finally realized that their technological masterpiece had to be abandoned for a new generation of all-big-gun battleships? The answers lie in the evolution of the American fleet, and the implications would fundamentally change how future American battleships were designed, leading to a move towards separate main batteries. But the question remains. If you were the engineer on that ship, faced with a design that looked perfect on paper but struggled in the cold, hard reality of the sea, how would you have navigated the clash between innovation and proven reliability? The year was 1895, and the United States was transitioning from an agrarian nation to an industrial titan. Across the Atlantic, the British Royal Navy possessed a fleet that could project power into every corner of the globe. American naval leadership, led by the intellectual fervor of men like Alfred Thayer Mahan, argued that the country's security depended on a blue-water navy. Mahan's doctrine, the influence of sea power upon history, had become the gospel for the U.S. government. Suddenly, the budget was there, The public support was there, and the desire to project strength was undeniable. But the American shipyards were still catching up. Constructors faced a unique constraint. The US government wanted ships that could cross the Atlantic, but also fit into existing dry docks. This meant ship displacement had to be capped. How do you cram the punch of a massive dreadnought into a hull that is 375 feet long? You innovate. And this is exactly where the Kearsarge design took a turn that would split the naval engineering community into two warring factions. The lead constructor was Philip Hitchborn, a man who believed that the future of the Navy lay in unconventional geometry. He was not afraid of the superimposed concept because, in the world of mathematical theory, it was beautiful. It used the vertical axis, something naval architects rarely dared to exploit. If you cannot make the ship wider, make it taller. If you cannot make the ship longer, stack the weapons. On paper, the Kearsarge-class looked like an absolute menace. Two 13-inch guns in a main turret, and two 8-inch guns sitting right on top of that same turret. The logic was that a single crew could operate both, saving weight and personnel. It was meant to be the Swiss Army knife of naval warfare. But the first red flag emerged during the preliminary design review. An influential group of officers argued that the blast pressure from the 13-inch guns would shatter the delicate instrumentation inside the 8-inch turret above. Hitchborn and his team performed rudimentary tests, claiming that the steel casing would protect the gunners and the equipment. They were convinced they had mastered the physics of blast pressure. They were so convinced, in fact, that they dismissed the warnings from the gunnery officers who actually had to handle these behemoths at sea. When the Kearsarge finally commissioned in 1900, it was the talk of the Atlantic. It was sleek, it was heavily armored. And it was the centerpiece of the US Navy's growing confidence. But the moment it pulled away from the pier, the internal tensions were already mounting. The sailors who manned the 8-inch turret were not just worrying about the enemy. They were terrified of their own main batteries. Imagine being in that 8-inch turret. You are effectively living on the roof of a 13-inch gun. You have no way to train your own guns if the primary turret is locked onto a target far to the port side. If the ship is engaging a target on the starboard side, your firing arc is limited. You are not a free-thinking weapon. You are a hostage to the main turret. Then there was the mechanical nightmare of ammunition loading. To get shells from the magazine into the 8-inch guns, the logistics chain had to pass through the main turret's rotation path. In a real-world scenario, the smoke, the heat, the panic, the deafening noise, every additional complication increases the chance of a catastrophic jam. And sure enough, during exercises, the hoists frequently lagged. The gunners were working in a space where they could barely stand upright, surrounded by the machinery of the primary guns below them. The US Navy had built a masterpiece of hubris, a ship that looked incredible in port, but felt like a collection of tactical compromises in the middle of a gale. Critics in the press and the professional naval journals began to whisper, "Why cannot we just build larger ships? Why are we settling for these weird compromises?" This internal debate reached the highest levels of the Navy Department. By 1903, the superimposed design was becoming a polarizing issue. It was not that the ships were failures. They were actually capable vessels for their time, but they represented an engineering dead end. The world of naval warfare was on the cusp of the dreadnought revolution. Britain was already experimenting with ships that abandoned secondary batteries entirely, favoring all big gun configurations. The Kearsarge ships were a perfect example of what happens when design engineers disconnect from the reality of combat. They had spent years building the future, only to find that the future was already moving past them. The ships remained in service for decades, but the superimposed turret design was never repeated on a large-caliber American battleship. It was a lesson in the dangers of over-engineering. Why does this matter now? Because history is a cycle of innovation and hubris. The engineers of the 1890s were not incompetent. They were ambitious. They were operating under immense political pressure to deliver a state-of-the-art fleet on a restricted budget. They made a choice that looked like genius in a calm drafting office, but proved to be a constant irritation at sea. As we look at the wreckage of these designs in the archives, we have to wonder, what were they thinking when they realized the mistake? Did they try to hide it? No. They kept the ships in service, they upgraded them, and they learned from the failure. They moved to the Virginia-class, and then finally to the all-big-gun South Carolina-class, which revolutionized the world again. The Kearsarge story is not a story of disaster, but a story of growth. It is the story of how the United States learned to stop trying to force impossible compromises and instead began to dictate the terms of naval power. It is a testament to the fact that sometimes the only way to find out what does not work is to build it, put it to sea, and watch the smoke clear. The final chapter for the Kearsarge was not a battle or a fire, but a slow, graceful transition into a crane ship, helping to build the carriers that would eventually win World War II. It spent its twilight years lifting the very machinery that rendered its own design philosophy obsolete. There is a deep, poetic irony in that. The ship that tried to redefine naval warfare ended its life as the humble servant of the ships that finally perfected it. So, when you see a piece of military technology, whether it is from 1895 or 2026, remember. There is always a human being behind the screen, a designer pushing the boundaries of what is possible, and a sailor praying that the blueprints hold up in the chaos of a storm. And that brings us to the ultimate question. In an era where technology evolves faster than ever, how do we balance the desire for revolutionary innovation with the reality of operational limitations? Is it better to build a flawed masterpiece or a reliable machine? That is the question that drove the Kearsarge designers, and it is the same question that drives every military engineer today. The transition from the late 19th century into the 20th century was marked by a relentless pursuit of speed, armor, and gunnery precision. The Kearsarge battleships were constructed at the Newport News Shipbuilding and Dry Dock Company in Virginia. The pride of the nation, they represented the pinnacle of industrial capability. When they were launched, the public cheered, newspapers hailed them as the most powerful machines on the planet, and the Navy's prestige skyrocketed. But look closer at the engineering journals from the period. You will find a fascinating narrative of engineers who were terrified. They were terrified because the transition from manual loading to hydraulic power was still in its infancy. They were trying to combine the reliability of traditional steam with the complexity of these new, heavy guns. The superimposed turret was the ultimate expression of that anxiety. It was an attempt to reduce the weight of the gun mounts to save space for coal, but it traded simplicity for complexity. The reality was that the gunners could not train the primary and secondary guns separately because the secondary guns were essentially piggybacked on the primary turret. Imagine being in a firefight where your enemy is moving at 15 knots and your gun system has a delay in rotation. The primary 13-inch guns were designed for long-range bombardment, while the 8-inch guns were intended for more rapid, shorter-range fire. By forcing them to share a mount, the designers had removed the versatility that was supposed to be the hallmark of the class. It is worth mentioning that during this same period, the U.S. Navy was developing its own internal fire control systems. The lack of independent train was a major handicap for the fire control officers who were trying to calculate solutions for two different gun calibers simultaneously. When they tried to fire the 8-inch guns, the blast effect from the 13-inch guns made it nearly impossible for the gun crews to maintain their composure or their accuracy. It was a classic design room error. The engineers had analyzed the static weight and the geometry, but they had ignored the human element. They had ignored the blast wave physics, and they had ignored the tactical reality of what happens when a ship is under stress. Some historians have argued that the Navy did not cover it up because there was nothing to cover up. The design was just of its time. However, the internal correspondence between the Bureau of Construction and Repair shows a persistent concern regarding the turret mounts. There were multiple reports suggesting that the secondary turrets were causing excessive vibration and strain on the primary turret's roller path. This was not a conspiracy. It was an ongoing engineering headache that simply did not have a good solution once the ships were built. The transition to the Virginia-class battleships actually continued the trend of superimposed turrets, which proves that the Navy High Command had not entirely given up on the idea. They believed that the problems with the Kearsarge could be fixed with better training and minor mechanical adjustments. It was not until the realization that long-range gunnery, the kind that would define the era of dreadnoughts, required independent, high-speed turret rotation that the concept was finally discarded. Think about the men who served on these ships. They were the ones who had to deal with the design limitations every single day. Their stories are rarely told. They were the ones scrubbing the decks, cleaning the massive guns, and dealing with the constant mechanical failures. They were the ones who knew, better than any engineer in Washington, that the ship was not as perfect as the newspapers claimed, and yet they operated these vessels with immense professionalism. The Kearsarge and the Kentucky were not failures in the sense that they did not work. They were successful in providing a platform for the Navy to learn what was possible. Every time a gun jammed, every time the rotation gear slipped, every time the ammunition hoist stalled, a new report was filed. Those reports became the blueprints for the future of the U.S. Navy. The lesson here is profound. Modernization is not a straight line of successes. It is a messy, iterative, often frustrating process. The Kearsarge was the price the Navy paid to understand what they needed for the next century of naval dominance. They were the lessons-learned vessels. When we look at the evolution of American sea power, we often jump straight to the Battle of Midway or the mighty Iowa-class battleships of World War II. But the foundation of those successes was built on the shaky, complex, and controversial turrets of the Kearsarge. The engineers who dared to think vertically, even if they stumbled, paved the way for the brilliant designers who would eventually make the American Navy the undisputed master of the seas. The question remains, are we still making the same mistakes? Do we still prioritize theoretical efficiency over operational reality? In an age of autonomous systems and digital warfare, the lessons from the Kearsarge are more relevant than ever. Technology changes, but the human element, the interaction between the sailor and the machine, remains the true test of any weapon system. The ships are gone, the shipyards have changed, and the guns have been replaced by missiles. But the spirit of innovation, the drive to build the ultimate weapon, and the inevitable clash with the realities of the sea, these are the things that never change. The Kearsarge-class battleships were not a mistake. They were a necessary step in the long, arduous journey to greatness. So, when you see a piece of military technology, remember, there is always a human being behind the screen, a designer pushing the boundaries of what is possible, and a sailor praying that the blueprints hold up in the chaos of a storm. And that brings us to the ultimate question. In an era where technology evolves faster than ever, how do we balance the desire for revolutionary innovation with the reality of operational limitations? Is it better to build a flawed masterpiece or a reliable machine? That is the question that drove the Kearsarge designers, and it is the same question that drives every military engineer today. As we delve deeper into the late 19th century naval doctrine, it becomes clear that the Kearsarge design was heavily influenced by the Jeune École school of thought, which originated in France. This strategy emphasized the use of smaller, faster vessels and heavy ordnance to overwhelm larger, more expensive battleships. American naval planners were fascinated by this concept because it offered a way to maximize their limited budget. They wanted the firepower of a behemoth on the frame of a smaller, more nimble ship. The decision to superimpose the 8-inch turret was a direct reaction to the perceived need for high-volume fire in close-quarters naval engagements. The designers were thinking in terms of broadside weight. If you look at the specifications of the Kearsarge, the broadside weight was indeed impressive compared to other ships of its size. But they had neglected the fact that naval battles were already beginning to shift toward longer ranges. The naval engagement at the Battle of the Yalu River in 1894, during the First Sino-Japanese War, provided the first major data point for modern naval combat. It showed that the speed and maneuverability of cruisers were less important than the ability to land heavy shells from a distance. The Kearsarge designers were trying to build a ship for a battle that was already becoming obsolete. This is the great tragedy of the design process. You are always building for the war that just ended or the war that you think is coming, but technology is moving so fast that by the time your ship is commissioned, the doctrine has already shifted. The Kearsarge was an attempt to solve the problems of 1890, but by 1900, the world was preparing for the challenges of 1910. Consider the political situation as well. The U.S. Congress was notoriously stingy when it came to naval appropriations until the Spanish-American War proved that the Navy was the country's most vital asset. During the design phase of the Kearsarge, the constructors were constantly being asked to reduce weight.